Before we start talking about Archimedes' principle, we want to cover the topic of air pressure. Air pressure. And one interesting question is, can I use a balloon as an altimeter? In other words, is there a way that air pressure changes with elevation, right? And what types of things would the air pressure affect? And one easy household item that a lot of people have easy access to would be something like a balloon. So here's how air pressure works. When you're at sea level, let's imagine this is the beach, so out here is the ocean, and you're standing on the beach. And you have in your hand a balloon, right? So I'm going to blow up the picture of the balloon. Here's the balloon, right? And what happens is, as you blow up the balloon, you put air molecules, or at least your breath, molecules into the balloon, and these molecules are flying around in here all at random directions. And what happens is they all exert a pressure on the edges of the balloon. And the result is that there's a net pressure everywhere inside the balloon acting against the edges. Right? So everywhere in the balloon there's pressure acting outward. Well, if there's pressure acting outward, then that should cause the balloon to expand indefinitely. But the pressure outward is mitigated by the pressure of the air at sea level acting inward. So when you have a fully inflated balloon, you have the situation where the pressure inside the balloon and the pressure outside have stabilized. They've come to an equilibrium, if you will. And what this means is that the pressure inside the balloon is the same as the pressure outside. Now, what happens if you were to, say, climb a hill? So let's say you started out with your balloon at sea level and then started to climb a hill. Well, at sea level again, your balloon is in equilibrium and you have air pressure pushing all around it, but this pressure is the pressure at sea level. And the pressure at sea level is much greater than the pressure at higher altitudes. So once you climb a hill, the air pressure acting against it is not quite as high. And so the pressure inside the balloon is now greater than the outward pressure, and so the balloon will expand until the pressures again come into equilibrium. So here at sea level, the pressure inside the balloon is equal to the atmospheric pressure, or PA, and here the pressure inside the balloon at its initial volume is greater than the atmospheric pressure up at a higher altitude. And so the balloon will then expand in volume until the pressures are equal. the pressure inside the balloon equals the atmospheric pressure. So in this way, you can kind of use your balloon as an altimeter because there is a direct relationship between altitude and air pressure. So you can actually use your balloon to measure the air pressure, and then you can deduce how high you are. So that's a little bit about how air pressure works. Now we want to turn to Archimedes' principle. And Archimedes' principle has everything to do with buoyancy. And I always misspell this word. Whoop. Buoyancy. Okay? Archimedes' principle has everything to do with buoyancy. Now there's a clever little story that goes along with Archimedes' principle and how he discovered this principle. And technically there should be an apostrophe there. But I think we're going to dispose of this story. It's cute and fun, but it's not completely relevant to the physics, so I won't take up your time with it. But the idea is that if I have a tank with water in it, and I submerge something, and let's say that it partially sinks and partially floats, what is the buoyant force pushing up on the object? And we can even write it as the buoyant force, right? And the source of the buoyant force is the change in pressure from the surface of the water down to the bottom of the object. There's more pressure. There's more water pressure or fluid pressure. It doesn't have to be water. It can be oil or gasoline or whatever. But there's going to be more pressure at the bottom of the object than there is at the level of the surface. And so it's that increase in pressure that's going to cause this buoyant force. So what does Archimedes' principle actually say? Archimedes' principle actually says that the buoyant force the buoyant force acting on an object fully or partially submerged in a fluid is equal to the weight of the fluid displaced by that object. Okay, so that's a heck of a sentence, and that's a lot to digest. So we'll break it down and describe just a little bit more about exactly what's happening here. So let's again look at our tank of water, and let's say that the tank is three-dimensional, of course, and let's let it be let's let it be cubic. So if we were to look at it from the sides, it would look like this. It would look something like that, except not quite so terrible artwork. Let's actually break that up. Let's clean that up a little bit. Okay, so it would look like this. And let's let it be oh, let's let it have equal dimensions on each side. Let's call it 20 centimeters by 20 centimeters, and then this depth, the length this way is also 20 centimeters. And let's say that we plop a piece of wood down that's also cubic in shape, right? And it is buoyed up by the buoyant force. And let's say that half of it is submerged, right? Let's say that half of the block is submerged. We want to calculate what that buoyant force is. Now remember that the buoyant force is equal to the weight of the fluid displaced. Okay? So what is the weight of the fluid displaced? Well, the weight of the fluid displaced, you can imagine the fluid displaced is equal to the volume of the object that is in the water. That is how much volume of water has been displaced. Well, how much of it has been displaced? Well, we need to know the dimensions of the block. And let's just let the dimensions of the block be 10 centimeters by 10 centimeters by 10 centimeters. So the height is 10 centimeters. The width here is also 10 centimeters. And the depth is also 10 centimeters. So if half of the block is submerged, that means that a height, this height here, is going to be 5 centimeters by 10 centimeters by 10 centimeters. So the volume of the submerged block is going to be 5 by 10 by 10, which 10 by 10 is 100 times 5, so 500 cubic centimeters have been submerged. Okay, so that's the volume. That means that the volume of water that's been displaced is also 500 cubic centimeters. Now, here's the trick, right? Remember that the weight is going to be equal to the mass of the water displaced times gravity, but here we have a volume. The trick is to note the density of water. So density is equal to mass over volume, right? Density is equal to mass over volume. And so water has a specific density. It is 1 gram per cubic centimeter, which is equal to 1,000 kilograms per cubic meter. And since we like our masses in kilograms, that's what we'll use. So we need to convert 500 cubic centimeters into cubic meters. And to do so, we just note that there are 1 million cubic centimeters in 1 cubic meter. And so this will give us 5 times 10 to the 4th cubic meters. Okay? So that's a negative 4. 5 times 10 to the negative 4th cubic meters. And so the mass of the water displaced is going to be equal to the density, which is 1,000 kilograms per cubic meter, times this 5 times 10 to the negative 4. And so this is going to give us 0.5. kilograms. I apologize, it's going to give us 0.05. 0.05 kilograms. So the weight is going to be 0.05 kilograms times gravity, which is 10. And so this is going to give us 0.5 newtons. So there, because this is the weight of the fluid displaced, or the water displaced, okay, this is the weight of the water displaced, therefore that is going to be the same thing as the buoyant force holding this block up. Okay, so the buoyant force is going to be, in this case, 0.5 newtons. Okay, so that is Archimedes' principle. What we want to talk about next is rates of flow of fluid. And this has to do with water flowing through a pipe. Or fluid flow anyway. But we typically think of water. So first things first, ignore the pipes and imagine a stream. So here we have a stream, and then imagine that somewhere downstream it contracts a little bit and then flows like this. So here we have our stream flowing this way, and we have a principle that acts on things like streams or pipes, and that's called continuity of flow. And what this basically says is, as long as no water is either leaking out of the stream via a tributary or none of the water is getting stopped up by a dam, then the continuity of flow says that the amount of water, let's say that I put a string across the river here and call this point A. Well, I'll put this on the next page and then we'll come back. Okay. Okay, so the continuity of flow essentially says that the amount of water flowing past point A must be the same as that flowing past point B. So if I look at another point downriver and call this point B, the total volume of water flowing past point A must be the same volume of water flowing past point B. But if the river constricts, okay, then that means the area, point B's area is smaller, and for the exact same amount of water to flow through point B as is flowing past point A, because the volume is smaller, the speed must be larger at B. Okay, so the speed must be greater through the smaller portions of the pipe than through the larger portions. And we can encapsulate this in a nice small equation, and all it says is that the rate of flow is equal to the velocity times the cross-sectional area. Now, what's the cross-sectional area? Well, imagine, now we will go to the pipes. Imagine that I have a pipe here, and I look at a block, and imagine it's full of water, all right? So it is completely full of water, and I just look at a segment of that water, and this water is going to have, if I just look at a cylinder of water, it's going to look something like this. Okay, and the cross-sectional area, if you will, the cross-sectional area is the area of the face of this disc. Okay, so it's the area of the face of the disc. So if I just look at a generic cylinder, and if the pipe is full, then it's going to be the area of the face of the pipe itself, right? So all of these areas are going to be equal. And so what this means is that if I have a pipe that goes from a large section down to a smaller section, so again, if I look at a point A in my pipe and I look at a point B in my pipe, my cross-sectional area at point A is going to be much larger than my cross-sectional area at point B. So we'll call this area A, and we'll call this area B. And area A is much larger than area B, therefore the velocity at A is going to be smaller than the velocity at B. Okay, that's all that equation says. Right? And that is true for completely full pipes. Right? That is true for completely full pipes. Now the last thing we want to talk about in this chapter is Bernoulli's principle. Okay. Now Bernoulli's principle is related to this rate of flow because it relates not only the velocities at the two different points in the pipes, but it also relates the pressures. So the pressure at point A and the pressure at point B. Okay? Now this is really a conservation of energy statement, and it'll look a little familiar to you, but it's written in a different form. And Bernoulli's principle says that the pressure at any given point in a pipe plus 1/2 times the density of the fluid, and we use, instead of D here, we use the Greek letter rho for density, times the velocity squared, so this is kind of like 1/2 mv squared, right? So this is an energy term, a kinetic energy term. But Bernoulli's principle says that the pressure at any point in the pipe plus 1/2 the density times the velocity at that point in the pipe must equal a constant. So if I look at point A here, okay, then I'm going to have pressure at point A plus 1/2 the density of the fluid times VA squared must equal a constant. But at point B, I'm going to have the pressure at B plus 1/2 the density times the velocity at point B squared, equal to a constant, and it must equal the same constant. So these two expressions are equal. So we can write PA plus 1/2 rho VA squared is equal to PB plus 1/2 rho VB squared. And now what we can do is look at some qualitative implications of this. So first things first, if we know that VA is less than VB via this relationship right here, we know that the velocity at point A is less than point B, what happens to the pressures? Okay, so if VA is less than VB, that means this term is going to be less than this term. So right now, this side of the equation wins, or is larger. To counteract that, that means that PA must be larger than PB. And in a sense, that makes sense because in the larger section of the fluid, there's more fluid, so the pressure exerted outward is going to be much larger than the pressure in the smaller portion of the pipe. But this is a little counterintuitive due to our everyday experience, because anybody who has a garden hose knows that if I have a garden hose and I have some water flowing out of the garden hose, and then I stick my thumb over part of the nozzle, I get spewage of water much faster and much greater. This is how a lot of people wash their cars. But the key here is a lot of people will mistakenly say that sticking your thumb over the nozzle increases the pressure. This is not the case. It increases the velocity because you're decreasing the area, the cross-sectional area, so the rate of flow must stay the same, so the velocity must push up, and because the velocity pushes up, therefore the pressure goes down. But you're not increasing the pressure. Okay, so the pressure in this situation does not increase. It actually decreases, but the velocity is what increases. Okay, so the velocity is what increases. And finally, I'll leave you with this thought experiment, and you can even do this at home. If you have a blow dryer, and forgive my artwork here, but imagine you have a blow dryer, okay, and this blow dryer is spewing air upward, so it's turned on, and it's spewing air upward. It's also going to spew air out this way, and air out this way. You can actually do this. You can set a ping pong ball right above the hairdryer, and it stays inside this air column. Why does the ping pong ball stay in the air column? And you can even tap it a little bit, and it will jiggle around, but it won't necessarily leave. So the issue is, okay, right above the middle of the hairdryer, in this region in here, you have high velocities. Because you have high velocities, that means low pressure. Because here on the edges, the velocities are not as high, that means you have high pressures. And it's that pressure exerting inward that helps stabilize the ping pong ball. So there you go. All right, so that is chapter 9, and we will start chapter 10 next time. See you then.